Hey everybody, sorry for the late start. I had a couple things to do. Welcome to class. Let's get the usual things going here. There's the chat. Let me pin my video. Let me give you guys the attendance form. I suppose I could like pin the attendance form link, but I don't know how to do that if it's even possible. So I clicked on there. I didn't mean to. Okay, cool. All right, what is up? I know that Sanders was talking about lots of things yesterday. He talked about continuity, I think, yesterday. Maybe that was the previous class. He also started talking about the limit definition of the derivative. So we can definitely talk about whatever you guys want. You can, or I can just start talking about what I think we should do. If you have any questions, well, let me know. You guys have any questions? I'm going to pull up the Sanders webpage here just so I can see if he's got anything specifically going on. A million things open. It's annoying. Sorry, one sec. Trying to get organized here. Nope, not you. Okay, I will do. That's fine. Sorry, let me see Sanders here. Has he posted another homework yet? Good question. Where did he post his homework? Oh, I'm in the wrong. I'm like, where is the homework? I'm looking at the co-class stuff. He doesn't post his homework there. Sorry guys, I didn't mean to be so behind the ball here. I just was trying to make a video for another class, and it took me a little longer than I thought because the math was hard. Okay, no, he's still got homework too. All right. Okay, so I've got some ideas. I think I'll just start saying stuff, but if you guys have questions, you know you can always speak up. So yeah, let's get going. There's the attendance again. Let me erase this. Also, just want to clarify, Sanders doesn't have any midterms, right? He's just doing quizzes. Is that correct? Okay, good. So that seems less terrible. So I feel like he kind of breezed through limits, and there's a couple more examples I would like to do just because I feel like they are things you should see. So I'm going to do, I didn't quite get to finish my my limit spiel. So there's just a couple more limits I want to do for you guys. And then we can talk briefly about continuity and then start talking about the limit definition of the derivative. So limits, I'm pretty sure we had talked about, so mostly I want to talk about 0 over 0 type of limits. And we definitely talked about the limit as x goes to 0 of sine of x over x, and how that was equal to 1. It's a really important one. And I'll come back to that in a little bit because there's something I want to ask you guys, although I haven't seen any on the homework, so my guess is no. And then we also started talking about the algebraic methods. And we had certainly done some factoring and canceling ones. So we had factored and canceled. And an example of that we may or may not come back to today is, say, like the limit as x approaches 5 of x squared minus 3x minus 10 over, sure, 2x minus 10. That's definitely a 0 over 0 type where we could factor and cancel. In fact, if you want, you should do that on your own at some point. I will tell you the answer comes out to be, I think 7 over 2. And then we also talked about multiplying by the conjugate. And an example of that could have been something like the limit as x approaches 2 of 3 minus the square root of x plus 7 all over 2. Sorry, not over 2, over x minus 2. So these are both examples of 0 over 0 limits that we could do. And maybe we will do them in a minute. But what I want to do is talk about the last method of algebraic kind of manipulation that we often use, which I might have put one like this on the quiz. I honestly don't remember, and I haven't graded the quiz yet. I'm going to try and get that graded today so you guys can get that feedback. But the last type is using a common denominator. So that comes up when you have like fractions in fractions. So an example of this would be something like the limit as x approaches, I don't know, 10. Let's see how I want to do this. 2 over x minus 1/5 all over x minus 10. So here's an example of a 0 over 0 limit. The top is definitely going to 0. 2/10 reduces to 1/5, and 1/5 minus 1/5 is 0. And the bottom, 10 minus 10, is definitely 0. So the way we're going to work with this, and so actually there's two different ways you can do this. I'm going to show you both. One way, kind of the standard way, is to just get a common denominator in front. So the standard way of doing this is to say, okay, well, I'm going to take 2 over x minus 1/5 all over x minus 10. Oh, don't forget to write the limit. The limit's super important. Man, I just opened a new black pen. It looks really good. Like, it's writing super nice. It really makes me happy. I know it's kind of dumb, but yeah, take what you will. So I'm going to multiply that by 5 over 5, and this by x over x. So I'm going to get the limit as x approaches 10. This is going to be 10 over 5x minus, this is going to be x over 5x all over x minus 10. And then we're going to write that top. Actually, I'm going to do one thing to kind of make it easier to see what I'm going to do here. This denominator, I'm not just going to write it as x minus 10. I'm going to write it as x minus 10 over 1. So that when I flip and multiply, I actually remember to flip it over. So I'm going to write this as limit is x approaches 10. The top, I'm going to combine this, right? The whole reason I got a common denominator, so I can write that as one fraction. 10 minus x over 5x times the reciprocal of this, which is 1 over x minus 10. 10 minus x and x minus 10 feel like they should cancel, but there's something not quite right there, and it's that they're actually opposites of each other. Right? If you subtract two numbers in the opposite order, 7 minus 3 is 4, 3 minus 7 is negative 4. And so when you divide things that are subtracted in the opposite order, well, 4 divided by negative 4 is negative 1. So 10 minus x and x minus 10, when you divide them by each other, you should get negative 1. And I typically just kind of cross them out and turn them into a negative 1. But what we can do, if we really, really want to, is we can factor out a negative 1 from the top. So I can write this as the limit as x approaches 10. We factor out a negative 1 and get negative 1 times, well, and then I'm going to have a negative 10 plus x. And I'm going to rewrite this whole fraction as just, right? When you have fractions times fractions, it's just the top times the top over the bottom times the bottom. So I'm going to write the bottom as 5x times x minus 10. And I don't multiply it out because I know I want this to cancel. So then look, this negative 10 plus x is really the same as x minus 10. So this cancels with that. And let's use my eraser here. This ends up equaling negative 1 over, I plug in 10 for the remaining x's, 5 times 10, which is negative 1 over 50. So that's the limit here. An alternate way of kind of attacking this is instead of doing 5 over 5 here and x over x here, so here's what I'll say. This way of doing it, I think, is it's the way that we usually think of doing it more easily. Like, oh yeah, common denominator. But there's another method that uses the common denominator that's just a little bit more algebraically easy. Also, I should ask, I put a lamp back there. Is that light in the back helpful or not? Like, let me ask you guys, does it look better that way, or does it look better if I turn it off? You guys are like, I don't care. I don't know. I can't really see if it's better or not, so. I like it better with the dom, but if you guys think it looks terrible, we can turn it off. Also, I guess I could open these shades and provide a little more light that way. There, probably a little bit better. Okay, so the other way we can do this is just instead of getting a common denominator, we can actually multiply the top and bottom by what the common denominator would be, which is 5x. Okay, thank you, Al. I appreciate it. So I'm going to multiply the top and bottom by 5x. In the denominator, oops, don't forget to write the limit. In the denominator, we're going to have x minus 10 times 5x. In the numerator, this is going to distribute 5x times 2 over x. The x's will cancel, and we'll get 5 times 2, which is 10. 5x times 1 over 5, the 5's will cancel, and we'll get minus 1 times x. And again, 10 minus x and x minus 10, they cancel out, but they leave behind a negative 1. So I really have the limit as x approaches 10 of negative 1 over 5x. And then plugging in 10, I get negative 1 over 50. So either way is the same. I just think the second method is a little bit more computationally easy, but the first way is a little bit maybe easier to remember how to do. Either way is fine. Are there questions about this? Okay. Seeing no questions. So let me ask you guys. Would you like to do these limits, or should we move on to something else? So I guess the question is, would you like to do these limits? Yes or no? Okay, I see some this. Also, if you don't want to say yes in front of everybody, it's perfectly fine. You can always send me a private message and say yes. That's also, or private chat. It's also perfectly fine. You can do whatever you want. So let's do these limits. I'll leave them up so I don't forget what they are. So this first one, and again, let me actually, I'm going to change it up just a little bit to make sure that so I'm going to do something slightly different and then we'll come back to this one. So let's say it was x squared plus 3x minus 10 over 2x minus, oh, I don't do that. Yeah, fine. I was going to ask something else, but that's dumb. No, I changed my mind. Let's not do that. Sorry. I thought I had a good idea. It was not a good idea. Let's just do that. So again, when you're doing these limits, you should always check to see if it's actually a 0 over 0 type of limit. So you plug in 5 here, you get 25 minus 15 minus 10, which is 0. Plug in 5 here, you definitely get 0. So it is 0 over 0, so we know we have to do something. So closer. I'm going to factor. And now here's the thing. If I plug in 5 and I get 0, then I know that x minus 5 should be a factor. So I'm almost certain x minus 5 is a factor. And then the other factor should be x plus 2. Because 2 and negative 5 multiply to negative 10, and 2 and negative 5 add up to negative 3. On the bottom, it's much easier. I'm just factoring out a 2. And then these will cancel. And you're left with the limit as x approaches 5 of x plus 2 over 2, which is 5 plus 2 over 2, which is 7 halves, or 3.5. I will point out, generally, in upper level math classes, calculus classes, whatever, we usually don't use mixed fractions. So it's fine to write it like this as an improper fraction, or like this as a decimal, but we really don't want to write it as 3.5. Because sometimes people can mistake that and think you mean multiplication, like 3 times a half. So typically we don't write it that way. If you really want to write it this way, you could write it as like 3 plus 1/2. That would be the best way to write it, 3.5, in my opinion. Okay, let me not erase this one before I actually do it. So limit as x approaches 2 of 3 minus the square root of x plus 7 all over x minus 2. So here the first step is to multiply by the conjugate. And so the conjugate, well, I should say which conjugate, right? The conjugate of the bottom is x plus 2. The conjugate of the top is 3 plus the square root of x plus 7. We definitely want the conjugate of the square root thing, so we're trying to get rid of the square root. So we're going to multiply by 3 plus the square root of x plus 7 over 3 plus the square root of x plus 7. Okay, I want you guys to do the next step. I want you to multiply at the tops and leave the bottom. In fact, I'll do the bottom part, but multiply at the tops and see what you get. I'll give you a minute for that. Okay, 1 minute precisely. If we were in class, we'd be walking around looking at your papers. Is the top 3 minus x plus 7? You're so close. It is minus x plus 7 in parentheses. That is correct. But we don't quite have just 3 here. What do we actually have here? Remember, you're multiplying these together. So you don't have 3, you have, 3 squared. It's always the first thing squared minus the second thing squared. And the place where I think some of you might have made a mistake, if you were doing this, act like it's just a place where people might make mistakes, not you necessarily, is remembering that you have to have parentheses around this here so you distribute the minus sign. Because it's this first thing squared minus this second thing, all of it squared. So it's minus all of that. And then things simplify. We get the limit as x goes to 2. The top is going to be, let's see, 9 minus x minus 7. And I would simplify that as minus x plus 2 over x minus 2 times 3 plus the square root of x plus 7. In my opinion, you can just say, hey, negative x plus 2 and x minus 2, those are going to cancel out and leave behind the negative 1 because they're opposites of each other. But if you don't like that, I would totally understand. You can factor out a negative 1 from the top. And so you've got the limit as x goes to 2 of negative 1 times x minus 2 over x minus 2 times 3 plus the square root of x plus 7. And then the x minus 2 and the x minus 2 cancel. And you get the limit as x goes to 2. So a lot of people at this point just plug in the 2. I'm showing all the steps, but it'd be perfectly fine here just to plug in the 2 for the remaining x's. So we get the limit as x goes to 2 of negative 1 over 3 plus the square root of x plus 7. We plug in the 2 for x, and we get negative 1 over 3 plus the square root of 9 is also 3, so we get negative 1/6. So that's how we would do that problem. Okay, so there's something I want to ask you guys, because I feel like there's a type of limit you might be seeing, but I haven't seen in this homework at all. So if we're not having to do it, I don't think we should spend time doing it. But if we are, I definitely want to mention it. So let me ask you guys, has he at all ever said or put on a quiz or on anything, the limit as x goes to 0 is something like sine of 7x over 3x? Have you seen anything like that where it's not just sine of x over x, but it's sine of a multiple of x over a different multiple of x? No. Okay. So here's what I want to say. If you do see something like this, let me know and we will cover it. But if you don't, then I don't think we really need to. I will say it's something that gets covered more in depth in other calculus series, specifically the 21 series, but also the 16 series. I don't think they talk about this as much in this class, so that's perfectly fine. More limits, or should we move? Actually, I think, unless you guys want to do more limits, let's move on to continuity. So, should we do more limits? All right. Looks like a no, or it looks like a no answer. Sorry, my carpet's all messed up here. Just one sec. Okay, so I know we talked a little bit about continuity before, so let's continue with continuity. And so the general idea with continuity is that, so let me actually draw some pictures, because this is kind of how people really think about it. So there's a few different ways a function can be discontinuous. I'm going to show you some examples. So, So let's look at this function, f of x equal to 1 over x minus 2. It definitely has a vertical asymptote at 2, right? Because if you plug in 2 for x, you have division by 0. And if you graph this, let's see. So if you plug in, the y-intercept is -1/2. So if you plug in 0 for x, you get -1/2 for y. And this function looks like this. And we could talk about the asymptotes if we wanted to. There is a vertical asymptote at x equal to 2. And we can see that because as you approach 2 from either side, the function actually blows up to infinity or negative infinity. In fact, we could definitely say that the limit as x approaches 2 from the right of this function, well, as we're approaching 2 from the right-hand side, the function is getting infinitely large. So that limit would be positive infinity, or just infinity. And the way I kind of write this when I'm doing it on my own is I say, okay, well, I've got 1 over a number. Well, let's see. If I'm approaching 2 from the right, I'm just a tiny bit bigger than 2, like 2.00001. And so when I subtract here, I don't really care what the number is. I just care that it's positive. Because a number that's a little bit bigger than 2 minus 2 is a little bit positive. And I like to write that like this. 0 from the right, meaning I'm just a tiny bit bigger than 0. Now here's the thing. If I have a non-zero number divided by a number that's very, very, very small, it's going to get infinitely large. Sorry, I'm not sure if I get away here. Right? 1 divided by 1/1,000,000th is a million. 1 divided by 1/1,000,000,000th is a billion. So this gets really, really big. The only thing is that sometimes it's negative and sometimes it's positive, right? Overall, this fraction is positive because the top is positive and the bottom is positive. So this is positive infinity. On the other side, the limit as x approaches 2 from the left of 1 over x minus 2. We can see from the graph that if we approach 2 from the left, then the limit's going to be negative infinity. And for the same sort of reason, I'm approaching 2 from the left and a little bit smaller than 2. And if you take a number smaller than 2 and you subtract 2, it's going to be a tiny bit negative. So I write this as a number that's just a little bit left of 0, a little bit negative. Again, when you divide a non-zero number by a really, really small number, a number that's really, really close to 0, it ends up getting infinitely large. But in this case, it's a positive divided by a negative, so the overall sign is negative, so it's negatively infinitely large. Again, the graph definitely shows us this as well. There was something else I meant to say here. Sorry, one sec. I had something, I think I lost it. Oh well. The other thing I want to point out, not that we really care in this instance, but I would say that the overall limit, oh, I know what it was, as x approaches 2 of this function does not exist. because the left-hand side and the right-hand side are going to different places, right? The left-hand side is going down to negative infinity, and the right-hand side is going up to infinity. If both sides were going up to infinity, or both sides were going down to negative infinity, then you would say the limit was whatever that was. And I know what that is. So the other thing I want to say was, someone asked me, I don't remember who, what the difference between the limit as x approaches 2 from the left is. So what's the difference between the limit as x approaches 2 from the left of your function and the limit as x approaches negative 2? And the difference is substantial, of f of x. So if you're approaching 2 from the left, that's when we're approaching 2 from the left-hand side, right? And we're going down like that. If you're approaching negative 2, that's when you're over here, which would just be that line there. So we already saw, in this particular example, the limit as x approaches 2 from the left of f of x is negative infinity. If x is approaching negative 2, just negative 2, we can actually just plug in negative 2 here. And 1 over negative 2 minus negative, 1 over negative 2 minus 2. Negative 2 minus 2 is negative 4, so you get negative 1/4. So very, very different. So approaching 2 from the left and approaching negative 2 are on totally different spots of the graph, right? Here is 2 from the left, and here is negative 2. So hopefully that clarifies that for whoever was asking. So this is one way that a function can be discontinuous, right? This function, f of x, is discontinuous. And here's some language that I want to point out. If someone asked about this function in general, if someone said, is this function continuous or discontinuous? I would say it's discontinuous. But what I really mean is that it's not continuous everywhere. It is discontinuous at 2, but it's actually continuous everywhere else. But if someone says a function is continuous, what they usually actually mean by that is they mean it's continuous everywhere. So this function has a lot of continuity. It's continuous at every single value of x except for x equal to 2. But it is discontinuous at 2. So hopefully that makes some sense, right? If someone said that the function is discontinuous, they really mean it's just discontinuous somewhere. And if they say it's continuous, they really mean it's continuous everywhere. Let's look at a couple more examples of discontinuity too. Oh, I know what I said. So here I would say f of x is discontinuous at x equal to 2. And I would say that the reason for that is because f of 2 does not exist. If I try and plug in 2, I don't even get a real number out. So that's one way a function can be discontinuous, is if you can't even evaluate the function at the point. So let's look at a different example. I should say, and sometimes that kind of discontinuity is because you have a limit like that, it's infinity. But sometimes it's because you have a function like this. Let's make it a little more interesting, James. X squared minus 5x plus 6 over x minus 2. Again, even without doing any work, I know that this function, I don't need to put a dot there. This function is discontinuous at x equal to 2. And again, because f of 2, if I plug in 2, I get 0 over 0, right? 0 over 0, yeah, 0 over 0. That does not exist. It's not a real number. It's indeterminate is what I should say. Now in this case, the discontinuity looks a little bit different. On the other side, this one was discontinuous at 2 and we had a vertical asymptote. On this side, this one's going to be discontinuous at 2, but we're not going to have a vertical asymptote. So here's what I want to point out. This function here does not have a vertical asymptote at 2. Because even though it's undefined at 2, that x minus 2 factor can cancel. This function is equal to x minus 3 times x minus 2 over x minus 2. Those cancel. And this is equal to x minus 3, except it's undefined at 2. So this looks like a line, the line y equals x minus 3, with a hole at 2. Oh, I just spilled water. Oh well, no big deal, just water. So this looks like the following graph. Y equals x minus 3 has a y-intercept at -3, an x-intercept at +3. It does this kind of deal. And then it's undefined at 2. So we should actually have a little hole right there at 2, -1. And so again, this function is discontinuous at x equals 2. I do want to point out though, it's discontinuous at 2, but the limit exists. If the limit as x approaches 2 of this function, x squared minus 5x plus 6 over x minus 2. Well, you can actually see how we find it, right? We would factor and cancel. So this would be the limit as x approaches 2. I mean, the graph is already showing us the limit's going to be -1, right? Because as we get close to 2, the y value is going to be close to -1. But we can also see it just doing the algebra here. This factors, these cancel, and then you plug in 2 for the remaining x, and you get 2 minus 3, which is -1. So here again, the function is discontinuous because f of 2 does. I should say the function is discontinuous at 2 because f of 2 does not exist. Okay, well I can try and fix that, and here I'm going to try and save myself some work. So I'm actually going to, so I'm going to change my function just a little bit, and let me write it in a different color to help you kind of show that it's something different. So instead, I'm going to make the function almost the same, but now my function is going to be a piecewise function. It's going to be equal to this, x squared minus 5x plus 6 over x minus 2, as long as x isn't 2. And when x is 2, darn it, I always drop this dumb eraser. And then I get gross stuff all over the floor. Sorry. I thought I'm going to grind this black disgustingness into the carpet. Also, I don't remember which class it was. I definitely dropped a red pen on the carpet the other day, but it cleaned up really well. So if it was this class, you saw me drop the red pen, no worries, cleaned up very nicely. Let's see. Let's say it's equal to, I don't know, 3 when x is equal to 2. The only difference between this function and the previous function is this function now at the point 2, the y value is now defined to be 3. And so now here's what we've got. The limit as x approaches 2 is still -1, right? As we get, use one of these red pens here. Sure. As we get closer and closer and closer to 2, the y values get closer and closer and closer to -1 from either side. So the limit is still -1, but the function value, well, we already know what the function value is. F of 2 is definitely equal to 3. So here, is the function continuous at 2? Yes or no? Anybody? I see someone wrote down. Okay. Sorry, just one sec here. Yeah, it's definitely not continuous. And again, I know Sanders has been talking about how like a function is continuous if you can draw it without lifting your pen off the paper. Well, you can see that here, right? To draw this one, you draw here, and then you have to jump up here and then back down there. So definitely not continuous at 2. This is a point discontinuity. The function exists. The limit also exists, but they're not equal to each other. So here we're failing to meet the definition of continuity, which is that the limit as x approaches 2 of f of x does not equal f of 2, right? Because we know f of 2 is 3, and the limit as x approaches 2 is -1, and those aren't the same. So this function is discontinuous because the limit and the function don't happen to equal each other, but they do both exist. So my general kind of, well, actually, let me show you one more example, and then I'll kind of give you a problem that I think is a pretty standard type of problem on the test. or on a quiz, I guess, because you guys don't have any tests. So let's see here. Let's say I want to find, so one more at 2. How about this function, f of x equal to 9 minus x squared when x is less than 2, and 3x minus 2 when x is bigger than or equal to 2. And so the question here, so here's the thing. I know each of these functions are continuous everywhere except for 2 for sure. I know this function f of x is certainly continuous everywhere except for 2. So it's continuous on the interval from negative infinity to exclusive and 2 to infinity. It might also be continuous at 2, but I know it's continuous at these other places because 9 minus x squared is a polynomial, and polynomials are continuous on their domains. So this polynomial is definitely continuous on x less than 2. And this polynomial, 3x minus 2, is also continuous on its domain, x bigger than or equal to 2. Now the thing is, at 2 specifically, since the left side and the right side might not be meeting up to each other, we can't say it's continuous at 2, even though 2 is part of the domain of this polynomial. So is it continuous at 2? Well, we need to check 3 things. We really only need to check one thing. So the thing we need to check is, does the limit, does the limit as x approaches 2 of f of x equal f of 2? But the reason I say we have to check 3 things is because we really first check, does this exist? Does this exist? And then if they both exist, are they equal? So if either one of them don't exist, we're done. The function's not continuous. If they do both exist, then we also have to check that they're actually the same. So here, does f of 2 exist? Yeah, it exists. Because I can plug into, am I plugging into to the top part of the piecewise function or the bottom part of the piecewise function? I'm sorry, if you guys tried to say anything, I think I might have my volume off. So if you want to say something and you've been trying to before, you're welcome to now. I think I have my volume off. Yeah, the bottom part, right? Because that's where x is equal to 2. So f of 2 is equal to 3 times 2 minus 2, which is 6 minus 2, which is 4. Okay? Now, how about the limit? Well, here, since the function is defined, I should say, does the limit as x approaches 2 of f of x exist? Right? And let me back up to the previous problem, right? That's definitely what we did here, right? We said that the function existed, we said that the limit existed, and then we saw that they weren't equal, so the function wasn't continuous. So here, does the limit exist? So let's take the limit from each side. So look at the limit as x approaches 2 from the right of f of x. That's going to be the limit as x approaches 2 from the right. Again, I'm going to be using the bottom piece because the bottom piece is where x is bigger than 2. And if I'm approaching 2 from the right, I am bigger than 2. So I'm using 3x minus 2. And this ends up being pretty much the same as what we did before. We're just plugging in 2, reading 4. But then I have to look at the limit as x approaches 2 from the left. The limit as x approaches 2 from the left. Well, if I'm approaching 2 from the left, I'm using the top part of the function because that's where x is less than 2. Less than 2 is left of 2. So limit as x approaches 2 of 9 minus x squared. I'm going to plug in 2 and get 9 minus 2 squared, which is 9 minus 4, which is 5. So what does this mean if the limit from the right is 4 and the limit from the left is 5? What can we say about the limit as x approaches 2 in general? Exactly. The limit does not exist. And once something doesn't exist, we know that the function is not continuous there. So this function is not continuous at x equal to 2. And here's what the graph looks like. So 9 minus x squared when x is less than 2. So here's the thing, right? When I'm left of 2, I know I'm approaching 5. So I'm going to look at the point 2 comma 5. Right, and that's what I'm going to get as I'm approaching 2. But it's actually not defined at 2 to be 5, right? If I plug in 2, I don't get 5, I get 4. So it kind of looks like this. Right, it's the left side of that parabola, 9 minus x squared, up until I get to the point 2 comma 5. It's an open circle there because I don't actually get that point. Sorry, I just kind of drew it like it was closed, but it's open. And then I get the other part, I get this line 3x minus 2, which has the point 2 comma 4. Actually, when I plug in 2, I got 4. So I'm kind of right there, and then it goes up like that. And clearly, it's discontinuous, right? I would have to take my pen off the paper or off the whiteboard to draw the graph. This is called a jump discontinuity. So, a question I would ask on the test. Is f of x equal to 3 times sine x over x when x is less than 0 and sorry, one sec. 2x plus 3 when x is bigger than or equal to 0 and less than or equal to 5. Sure, and then the square root of x plus 4 when x is bigger than 5. So the question I want to know is f of x continuous at 0, continuous at 5? Right, the places where we break from one piece of the piecewise function to the other piece are the places where we usually ask, oh, is it continuous there? So I'm going to go through my usual steps. I'm going to check if the function exists, the limit exists, and then they're equal. And if any of those things fail, it's going to be not continuous at that point. So f of 0. If I plug in 0, I'm picking the middle piece because that's where x is equal to 0. And I get 2 times 0 plus 3, which is 3. Okay, f of 0 exists, so I move on to, does the limit exist? So I'm going to look at the limit as x approaches 0 from the right, and the limit as x approaches 0 from the left. And usually I write that the limit as x approaches 0 of f of x, but I'm just going to plug in the piece of the function. So we're approaching 0 from the right. Actually, this is a good question. So I'm doing the limit as x approaches 0 from the right. Should I be using the top, the middle, or the bottom piece? I definitely know it's not the top piece. It is the middle piece. And I want to kind of say this a little bit more strongly. I've definitely seen some people in the past use the right-hand piece because they think, oh, if I'm bigger than 0, it can be anything. But it's not just that I'm bigger than 0, it's that I'm specifically bigger than 0, but getting close to 0. This piece doesn't get close to 0, right? It says x is bigger than 5. So we wouldn't use this piece. We definitely use this piece where x is bigger than 0, and we're actually getting close up to 0. So I'm going to use the piece 2x equals 3. And this limit's easy. I just plug in 0. I get 2 times 0 plus 3, which is 3. So I have to look at the limit from the left. If I'm approaching 0 from the left, I'm definitely using this piece with that domain. That's going to be 3 times sine x over x. Now, when you have a constant multiple, you can just put that in front. So I can make this as 3 times the limit as x goes to 0 of sine of x over x. And what's the limit as x goes to 0 of sine of x over x? It's definitely 1. So we get 3 times 1, which is 3. And look, the function exists, the left-hand limit and the right-hand limit are the same, so the limit exists. So this means, right, so together these things mean that the limit as x approaches 0 of f of x is equal to 3. And then, since the function is 3 and the limit's 3, since they're the same, we get to say that the function is continuous. So then I just do something like f of x is continuous at x equal to 0 because the limit as x approaches 0 of f of x is equal to 3, and that's equal to f of 0. So this function is continuous at 0. The function exists, it's equal to 3. The limit exists, it's equal to 3, and the function and limit are equal to each other. Let's see what time is it. Okay, we got enough time to finish this off. So I'm going to erase this so we can do the other one on this board as well. So I'll leave that bottom part there for now. So same steps. I'm going to look at f of 5. So if I look at f of 5, plugging in 5 again to the middle piece, because that's where x is equal to 5, I get 2 times 5 plus 3, which is 13. Looking at the limit. Now here's something I'll point out. If you did the limit as x approaches 5 from the right of f of x, you would get the limit, as x approaches 5 from the right of the square root of x plus 4. You could plug that in, and the square root of 5 plus 4 is the square root of 9, which is 3. And now here's the thing. I know at this point it's not going to be continuous because the function is equal to 13. And one of the one-sided limits is 3. So either the other side limit is going to be 3, and the limit exists, and the function is not continuous because the limit's not the same as the function value. Or the other side of the limit is going to not be 3, and then the function is not going to be continuous because the limit doesn't exist. So either way, once this is different than one of the one-sided limits, we know it's not going to be continuous. Now, I still think you should find the other side limit so you can say how it's not continuous, right? I want you to tell me, at least if I'm your teacher, is it discontinuous because the limit doesn't exist, or is it discontinuous because the limit exists but it's not equal to the function value? So let's go ahead and do the other side real quick. So limit as x approaches 5 from the left. I'm using this piece, right, because that's where x is less than 5. So I've got 2x plus 3. I plug in 5, sorry, that's a plus, and I get 13. And so I can see, oh, look, these aren't the same, so the limit doesn't exist. So this function is discontinuous at x equal to 5 because the limit as x approaches 5 of f of x does not exist. So that might not be completely required by your teacher, but I do think it's good to be precise and think about, oh, why is the function actually discontinuous? But, yeah. All right, that's all I've got for today. If you have things you want to see on Friday, let me know. Feel free to start a discussion in Canvas. Oh, and make sure if you didn't get to it, please do fill out the attendance form. Whoops, that's not what I meant to do. Sorry, I want to send it to everybody. Cool, there's the attendance form one more time. Please make sure you fill it out. All right, I'm gonna end the meeting now. So hopefully you've all had a chance to get that. Have a nice Wednesday.